Hello, good morning students. Yesterday we have seen what is the performance equation of equal size mixed flow reactors. Today we are going to see the next point, mixed flow reactors of different size in series. So first of all we are going to see how to decide the maximum conversion for a given system. Suppose we want to find the minimum size of two mixed flow reactors in series to achieve a specific conversion of feed which reacts with arbitrary but known kinetics. Consider two alternative reactor arrangements as shown below. Okay, now here you can see the figure A represents the small reactor followed by large reactor. And B represent large reactor followed by small reactor. This is case A1. Here you can see this is a small reactor followed by a large reactor. So V1 is less than V2, and this is a system B where large reactor is followed by small reactor. So V1 is greater than V2. If we have these two systems, then I can write the performance equation of first reactor, that is tau 1 by C0 is equal to x1 upon minus R1. The performance equation of any reactor I we have already seen in the previous lecture. So tau by C0 is x1 minus x0 upon minus R. Here x1 minus x0 is 0 here, that's why it is not written here. So x1 upon minus R1. This is the first reactor, so rate of reaction will be minus R1. Similarly, if I want to write for second reactor, I can write tau 2 by C0 is equal to x2 minus x1 upon minus R2. So x2 is the conversion in the second reactor, minus x1 is the conversion in the first reactor upon minus R2. R2 represent the rate of reaction in second reaction. So this will be the performance equation for second reaction. Now if we draw the graphs, we will get something like this. Now here you can see this is the first system where small reactor is followed by large reactor. This is the second system where large reactor is followed by small reactor. So if you see the first system, you can see here x1. Since small reactor you will get a less conversion, and after that it is followed by large reactor, so you will get more conversion. Similarly here this is a large reactor, so you will get more conversion, and then we have small reactor, so you will get less conversion. This represent 1 upon minus RA upon x1. So with respect to conversion, how the rate of reaction will change. We have already studied in the chapter number 4 how to find the area of MFR. So here if I want to find the area of MFR, then it represents the shaded curve NM0 and x1. If I want to see the area of second reactor, then I have this rectangle. So this will be the area required for second reactor. Similarly for case 2, this is the area of first reactor, and this is the area of second reactor that we want to study. So all these shaded area represent how much size of reactor 1 and reactor 2 required for both the systems. Now if you see this rectangle, that is KLMN, and here KLMN, this is the shaded portion which is not required for the reaction. Now imagine this is the total size, this is the total size. x2 is same for both the reactors. At x2 rate of reaction will be same for both the systems. So the size of this rectangle will be same for case 1 and case 2. Okay, now if I want to minimize the size required for a given conversion, then I have to find out where is this size maximum possible. If system 1 has a maximum size, then I am going to select this because it requires total area of reactor less here. But if system 2 is greater, then I will say I will go with the system number 2. Means our objective is to maximize the area of rectangle KLMN. I want to maximize the area of this rectangle so that area required for reactor 1 and area required for reactor 2 will be minimum possible. To do this, what we can have, see this curve. Okay, now here you can see the curve. Again it's 1 upon minus RA upon versus x. Here we have x1 and x2. This is the rectangle we are going to look out for. Now if I want to minimize the area of this reactor and this reactor, I want to maximize the area, this empty area. When we can say this empty area will be maximum when this area is area of a square. Now how to find the area of square? For that I have to optimize the value of x1. Means I have to decide the point on this curve in such a way that if I draw the tangent on this curve and the diagonal of the rectangle, both should be parallel to each other. If I get both parallel to each other, then this line and this line will be same and you will get the area of square. So square has a maximum area as you have studied in the geometry. So I have to decide where will be my point x1. If I can decide point x1, then I can find out what will be the size of reactor 1, what will be the size of reactor 2. This is called maximization of rectangle. If I find x1 in such a way that this is a square, then I get minimum volume possible for reactor 1 and reactor 2. Then only I can say we can get the same conversion, that is x2, for this system with a minimum size of reactor. So this is called maximization of rectangle. Okay, now we have already studied these equal size and unequal size mixed flow reactors. Now we will solve one problem to find out what will be the size of reactor and how to decide the economics. So here you can see the problem. I will read the problem. The kinetics of aqueous phase decomposition of A is investigated in a 2 mixed flow reactors in series, the second having twice the volume of first reactor. At steady state with a feed concentration of 1 mole of A per liter and mean residence time of 96 seconds in the first reactor, the concentration in the first reactor is 0.5 mole of A per liter and the second is 0.25 mole of A per liter. Find the kinetic equation for the decomposition. So they have given this system. I have drawn the diagram here. So here you can see we have a reactor 1 and we have reactor 2. What they have mentioned, the kinetics of aqueous phase. Aqueous phase means liquid phase reaction. A means we are having a single reactant in a 2 mixed flow reactors in series. So we are having 2 mixed flow reactors. They have mentioned the size of second reactor is twice that of first reactor. So here you can see the size of second reactor is double than that of first reactor. At a steady state means inlet and outlet volumetric flow rate remains same. What they have mentioned, that the concentration, feed concentration is 1 mole of A per liter, means C0 value is given and mean residence time of 96 seconds, means tau 1 is given for reactor 1. The concentration of first reactor is 0.5 mole of A per liter, means what, value of C1 is given, and in the second reactor is 0.25, means what, value of C2 is also given. Based on this data, we want to find the kinetic equation for decomposition. Okay. So consider the rate of reaction is minus RA is equal to Kca raised to n. Why we are written only single reactant? Because they have mentioned only A, means A is going to react to produce the product, and order we don't know, that's why we are written exponential with respect to n. Now we have to determine the value of K and n because these are both unknowns, and to find two unknowns we have to find two equations. So for that, this is a given data as I already mentioned. C0 is equal to C0 is equal to 1 mole of A per liter, C1 is equal to 0.5 and C2 is 0.25 mole of A per liter. Now for, if you see the reactor 1, I can write the performance equation of reactor 1, which we already studied in previous lecture. Tau 1 is equal to C0 minus C1 upon minus R. So C0 minus C1 as it is, minus R1 means what is the rate of reaction in reactor 1, which I can write as K Ca raised to n. Here you can see K C1 raised to n because concentration in first reactor will be C1. For similarly for reactor 2, I can write tau 2 is equal to C1 minus C2 upon minus R2, and minus R2 you can see K C2 raised to n. Why C2? Because concentration in reactor 2 will be C2. Okay. Okay, now tau for CSTR1 is given 96 seconds. Since this is a liquid phase system, mean residence time is same as space time. So, and also they have given volume of CSTR1, I am going to assume V1, and they have also mentioned that the second reactor is twice than that of first reactor. So I can write for volume of second reactor it's twice V1. And also we know that tau is equal to V by V naught, that is volume upon volumetric flow rate. So if I do tau 1 by tau 2, that is a space time in first reactor upon space time in second reactor, I can write V by V with respect to 1 and V by V naught with respect to 2. And if you substitute, what we will get, here you can see tau 2 is equal to 2V by V into tau 1 is equal to 2 into 96, because the space time in the first reactor is 96, so space time in the second reactor will be 192 seconds. Okay, now we got all the unknowns. So if we substitute in the equation, you will get this. Here you can see what we have done. We have taken the ratio of equation 1 to equation 2. So tau 1 by tau 2 is equal to C0 minus C1 upon K Ca raised to 1. This is equation 1, and K tau C2 raised to n upon C1 minus C2, that is equation number 2. If you simplify this, you will get C0 minus C1 upon C1 minus C2 into C2 by C1 raised to n. Now if you substitute the values, you will get this. So tau 1 is 96 seconds, as you already know. Tau 2 is 192 seconds. Concentration, initial concentration C0 is 1, C1 is 0.5, C2 is 0.25. So if you substitute all the values and calculate, you will get the order of reaction, and the order of reaction is 2. Similarly, if you remember the equation 1, that is K is equal to C0 minus C1 upon tau 1 raised to C1 raised to n. Now since we know the value of n, I can substitute and you will get the value of K. So if I substitute the value of K and n, you will get the performance equation of reaction in unequal size mixed flow reactor.